Yes, it's Uncle Jegs. Today's video is all about the density required practical. We will first deep just how small particles are. Then we will look at the theory on density, and finally, we will move on to the required practical. As always, check out the timestamps below to skip to exactly what you need and get the worksheets for today and also the answers to the previous video's worksheet. Alright, let's keep that thing. Jaguars to Jupiter, freckles to fufu, all the stuff around us and inside our bodies are made up of ridiculously small atoms.
How small, Uncle?
That's a bit of a mad one still. Let's put these numbers into perspective. We're going to use standard form and prefixes, so if you haven't watched my videos describing them, click on the link to get up to speed with all of that. The width of the largest hairs on your body is roughly around 200 micrometers. Since 1 millimeter is 1,000 micrometers, we can divide this by 1,000 to get 0.2 millimeters. Cool, that isn't too crazy. You can pull out a ruler and see the millimeter marks and wrap your head around all of that. However, keep that ruler next to you, my G. We can write 0.2 millimeters as 2 times 10 to the power of minus 4 meters in standard form. Notice that the standard form version is in meters and not millimeters. This is the width of your hair in meters instead of millimeters. An atom is roughly 0.1 nanometers. Since 1 millimeter is around a million nanometers, we can divide our 0.1 by 1 million to get 0.000001 millimeter. Putting this into standard form, we get 1 times 10 to the power of minus 10 meters. Remember that your hair is 2 times 10 to the power of minus 4 meters. That means that the width of your hair has 4 zeros in front of it, and the atom has 10 zeros in front of it. When we cancel out the zeros, this leaves us with 6 more zeros left over here. That means that an atom is roughly 1,000,000 times smaller than the width of your hair.
Uncle, not gonna lie, you're starting to waffle a bit.
Fair enough. You've been to the O2 Arena before, right?
Yeah?
Imagine if you made an atom the same size as the width of your hair. The width of your hair would take up the space of the O2, the Thames, and even the surrounding area by this much.
That's how big my hair is compared to an atom? Rah! Even the Tesco, you know?
So regardless of your taste in music, whether that's Stormzy, Celine Dion or Elton John, when you're in the arena and your hair starts to stand on ends, just look at one of those hair strands and deep the difference in size between the hair that you can see and the atoms that you can't see that make it up. It's mod. Alright, enough waffle. Have a look at these two images and answer these questions. Which of these two is heavier and which would you expect to float? You should have clocked that the ship is both the heavier object and also the one that will float. The same way that icebergs float on water because they're less dense than water, the ship as a whole is less dense, but the pound coin on the other hand is more dense. This is the equation. Density is equal to mass over volume. Mass is measured in kilograms, volume is in meters cubed, and therefore density has to be kilograms per meters cubed. Calculate the densities of these two objects using these values. The mass of the pound coin is 0.00875 kilograms, and the volume of the pound coin is 0.00000012 meters cubed. The mass of the ship is 60 million kilograms and the volume of the ship is 404,634 meters cubed. Pause the video and try and work it out. Mass over volume is density, so the density of a pound coin is 7,292 kilograms per meters cubed, and the density of our ship is only 148 kilograms per meters cubed. Therefore, the pound coin is a lot more dense. That must mean that the density of water is somewhere in between the two values, lower than the coin but higher than the ship. And the density of pure water is actually 1,000 kilograms per meters cubed. So as long as you know what the volume and the mass of the object is, you can work out its density. And we can work out the mass of anything just by placing it on a digital scale. For regular objects like cuboids, we can find the volume by multiplying the length, width and height. So in this example, 2 times 2 times 2 gives us 8 meters cubed. However, if you've got an irregular object, we need to use a displacement can to work out its volume. Displacement cans work because the liquid that is displaced by the object, the volume of that liquid, is equal to the volume of the object. If I pour water into this box, the space that's taken up by the cube is equal to the space that the water would have taken up if the cube wasn't there. That's why when you take a bath and you step into your bath, the water rises. Your body is taking up the space that water would have taken up if your body wasn't there. Okay, it's time for the practical. This practical has 3 parts. We will be investigating density of irregular objects, regular objects, and also liquids using a range of different apparatus. The first activity will have you determining the density of regularly shaped objects. First, start by measuring the length, width and height of each of your object. Calculate the volume by multiplying the length, width and the height of each. Record your results in a table like this one here. Measure the mass of each object and then record that in your table as well. And then all you have to do after that, since mass over volume gives you your density, you just work out your density like that. Boom. The next activity now is all about determining the density of irregularly shaped objects. The first thing you do is you measure your mass for each of your objects. Then you put a displacement can on your desk. Have your container ready to collect any water that comes out of your displacement can. You're going to fill the displacement can with water until water starts pouring out of the nozzle over here. Now you place a measuring cylinder next to your displacement can. You carefully lower your object so that it's completely submerged. You collect all of the water that comes out of your displacement can. You carefully measure the volume of water that's been displaced from your object, and now you know the volume of that object. And since you worked out your mass already, mass over volume, you can work out your density. You repeat that with all the other objects that you're going to measure, and don't forget, you have to keep refilling your can each time. The final activity will have you determining the density of a liquid. The first thing you do is measure the mass of your empty measuring cylinder and then record it in a table like this one here. You pour 100 centimeters cubed of your liquid into the measuring cylinder. Measure and record the mass of the measuring cylinder after you've added your liquid. You take this mass away from your initial mass, which was just a measuring cylinder by itself, and this gives you the mass of your liquid by itself. Use this mass and the volume that you just measured to calculate the density, mass over volume. This will give you a unit in grams per centimeters cubed. To convert that to kilograms per meters cubed, you just multiply your answer by 1,000. And that, ladies and gentlemen, is it for this video. Check out the work in the description, and if you're still baffed, use the timestamps to skip to what you need to. Like, comment, bell and all that jazz, and don't forget that science is more than just a body of knowledge. More importantly, it's a way of thinking. Think big in a bit.